Hello, welcome to our third lesson on fluid dynamics. Okay, so in this video we'll talk about steady viscous parallel flow, like I've stated here, and we'll be looking at the flow of a fluid between two parallel plates. Okay, what are the actions that are happening within this? Okay, so if you've not subscribed to my channel yet, kindly subscribe for more videos in the future. All right, so let's start. So if I have these two plates like this, okay, I have these two plates like this one, okay, and this one, and I want to know how the fluid properties like velocity here. If you see u here, this one is velocity. Okay, if you see u of something, that we are talking about velocity, right? Okay, see that the flow is just between the height of the two plates. Okay, so in a Cartesian plane, let's say we are calling this height y. Okay, from this side to this side. Okay, let me use another pen. Okay, let's say let me use a red pen. From this side to this side, we are calling it y. Okay, so it means that this flow is like the fluid is just moving up and down, just within the vertical lane. Okay, all right, so if that is the case, then we are applying a condition here that we call the no slip. Okay, let me write it well for you. The no let me use a white pen. Okay, saying that the no slip, okay, no slip condition. Okay, and the no slip condition at the part where we have the maximum height of y. I mean, if you consider these two plates, you see that this is the down one is at the bottom, and then this one is at the maximum height. Okay, so the no slip condition is saying that at the maximum height, the velocity at that height where we have a maximum height, that is y maximum, is equal to 0. That is what we have here. Okay, and at the minimum, meaning at the ground, okay, or at the place that is below, at that place too, we have the velocity to be 0, and at that place we've not moved any height on the y-axis, so it means that our y at that point to be what? 0, and the velocity there is also 0. Now if you go through the derivation of this whole equation here, we'll come back and get a formula like this that I have here. Okay, you have d tau dy equals dp dx. Okay, now this tau here that you see in this equation, okay, let me erase something. All right, so this equation, the tau you see there is actually shear stress. Okay, shear stress, and the y is the dimension where we are moving in. So you can see that just this flow is just between the y axis, only it's just moving up and down. Okay, so it's like just a one-dimensional flow. Okay, that means that this is the area. Okay, the area that we are moving with respect to. Then the del p del x is actually the pressure gradient. Okay, it's called a pressure gradient. Okay, so just keep this in mind. Okay, a pressure gradient. Okay, so that is it. So these will be the equations we can get in. Now from these equations and then the no slip condition, we can derive some other formulas. We are interested in the shear stress and then the the fluid velocity. Okay, so let's continue to our next slide so that we can derive our velocity for the fluid. Okay, now we are saying that this is the formula we will get out of the diagram we just discussed. And if you remember, in our previous video we discussed something called the Newton's law of viscosity. We said that for a given displacement or for any angular deformation, shear stress is directly proportional to what? the viscosity. Okay, and I said that we should keep that in mind. So it means that always shear stress is given by this in terms of fluid velocity and shear stress. Okay, so if that is the case, then from this equation, let's say if I call this equation 1 and I call this equation 2, I can put equation 1 in equation 2 in the sense that wherever I see my tau, I put mu du dy there. So I have d dy of the tau, which is what? Mu, okay, du dy, and this should be equal to, let's say, del p del x. Okay, that is how the formula is being written as. Now with this, mu is a constant, so I can get my mu out, then d dy, okay, of du dy again, okay, and this should be equal to del p del x. Now with this, I get my mu, then d squared u dy squared should be equal to dp dx. Okay, so I have d squared u dy squared is equal to 1 over mu dp dx. Okay, so now this is the differential equation of the second differential equation of u, that is the fluid's velocity with respect to the dimension we are moving in, which is the y. Okay, so now with this, how do you solve this? This is a very simple differential equation in one dimension. Okay, so it's just an ordinary differential equation. All right, so let's erase this part. Okay, erase this part, and I hope you understand what we are doing here. Okay, to just find velocity, okay, in terms of the y and the mu. Okay, so if I want to do this, then it means I have to integrate both sides, all right, with respect to y 2 times. Okay, so first integral will give me du dy at the first part. Okay, now I'll get 1 over mu. Actually, it's like d squared u equals, you make d squared u the subject, but then I want to just draw it straight away for you. Then we get dp dx, and I'll have my y, okay, because we are integrating with respect to y, then plus c1. Okay, then I'll have another different integral which will give me u of y, and this should be equal to 1 over 2 mu, because I'm integrating with respect to y, and when I integrate y here at this point, I'll get y squared over 2. So I just do it straight away for you, dx, then y squared plus c1 y and plus c2. I hope you get it now. So this is our new equation for our velocity. That's the fluid velocity is now given as u of y is always equal to 1 over 2 mu del p del x y squared plus let me write the square y squared plus c1 y plus c2. So this is our new equation for discussion. Okay, so this is what we have. All right, so now what is my c1 and my c2 and the rest? Okay, now we know that we first discussed something in our first slide, that for the no slip condition, the velocity at the maximum height, and always remember that the maximum height will be given. We are saying that u of y max is always equal to 0, and u of y equals 0, that is at the minimum length or the minimum height, which is 0, meaning the velocity at the starting point, okay, where we've not moved, is equal to 0. Then it means that putting my y equals 0 in this equation, this one, you have u of 0 is equal to, and put y equals 0 in every place, y squared, I put y equals 0 in place of here, I'll get 0. I'll come to the c1 aspect, I'll get 0, so I'll get c2 and we are saying that u of 0 is what? Equal to 0 from here. So it means c2 is equal to 0. Now I come to my c1. So it means the whole velocity equation tends to be something like this: 1 over 2 mu del p the x y squared plus c1y. Okay, so this is what we have. Now it's up to us to find we are supposed to find c2 as c1. Already we know c2 to be 0, right? So let's erase this place quickly and then talk about c1. Now to find c1, I said you have to apply the no slip condition. Okay, alright, so applying the no slip condition, we know that u of ym, and this will be given always, is also equal to 0. So I put ym in place of wherever I get. I'm saying that u of ym is equal to 1 over 2 mu del p del x, then ym squared plus c1 ym. But we are saying that this side is what? 0. So I have 0, then minus 1 over 2 mu del p del x, okay, y squared m should be equal to c1 ym. Okay, so my c1 is equal to, dividing through by ym, and I'll get negative 1 over 2 mu del p del x ym. Now I come to this equation, okay, this one, and I put my c1 there, and that will be my velocity. Okay, so let's erase some parts of our board and then write it quickly there. Okay, so right now we know c1, we know our c2 to be 0, and of course that has given us a simplified form of our velocity. Okay, so our u of y is now giving us 1 over 2 mu del p del x y squared, okay, then plus c1, but c1 is what? Negative, so minus 1 over 2 let me write it down here. So minus 1 over 2 mu del p del x, then ym times y. Okay, so how do we go about this? We can factor some terms out. Okay, we have 1 over 2 mu del p del s in both terms here in this equation. Okay, so we can quickly factor some terms out and simplify our velocity like that. Okay, so now our final fluid velocity is given as what? U of y is now equal to 1 over 2 mu del p let me write it well for you, del p del x into y squared minus ym y. Okay, so this is the final answer for our fluid velocity. So whenever we are dealing with a parallel viscous flow and we are being asked to find the fluid velocity u of y, then is equal to 1 over 2 mu d del p del x times y squared minus ym y. Okay, where y will be there, that one dimensional way that we are flowing. Y will be the height actually that will be given to us, or the distance between the plates. Okay, now since we know our velocity, let's go and then find our shear stress. Okay, all right, so our shear stress is that, but we know that our velocity u of y is equal to what? since the shear stress is what mu times du dy, okay, but our u is what 1 over 2 mu, okay, 1 over 2 mu del p del x, then we have y squared minus ym y, okay, and we are saying that our shear stress is simply just differentiating this whole thing multiplied by mu with respect to, so we are just using this, so it's just mu times del, or d, let me use the d straight, d dy, okay, of the whole of what u of y. But now if I'm to do everything, then it's mu times, then I'm differentiating u of y given like this with respect to y straight away. When I differentiate, already 1 over 2 mu del p del s, they're all constant, so I just multiply by 1 over 2 mu del p del x, then I differentiate the brackets and I'll get something like 2y minus ym, everything with respect to y, okay. If you differentiate y, you get 2y. If you differentiate ym, mind you, is a number, okay, it will be given to you. Alright, so this mu can take this mu out, and I'll be left with shear stress being equal to, half, okay, let me write it well for you, half del p del x into 2y minus ym. So this is my shear stress, always for a parallel viscous flow, okay. So just keep these formulas in your mind. We'll solve a very big question, one strong question under this after our discussion, okay. So just stay tuned. All right, let's move on to other concept. Okay, so u max. Now we are supposed to find the maximum velocity, and we are saying that the maximum velocity occurs at y equals y over 2, okay. Now let's record that our u y is given as 1 over 2 mu, okay, del p del x, then y squared minus ym y, okay. And we are saying that we want u max, so let me call it umx, and this should be equal to 1 over 2 mu del p del x. Now we are saying that at the maximum velocity y is equal to ym over 2, so wherever I see y, I put ym over 2, so ym over 2 all squared minus ym dot ym over 2, okay. Now this will give me 1 over 2 mu del p del x, okay. Now I have ym squared over 4 minus ym squared over 2, okay. So solving whatever that is in the brackets, what do we get? Let me erase this part for you. Let's solve the fraction there. Everything is, we have ym at both, so u max, okay. Now u max, let me come and write it here. U max should be equal to the same 1 over 2 mu del p del x. Now if I solve the brackets, I'll get something like I have 1 over 4 minus 1 over 2, so it's like 0.25 minus 0.5, and in the end is the same as 0.25, sorry, negative 0, so you have minus ym. If you solve this fraction clearly, this is minus ym squared over 4, this is what you will get. And then it means that u max will be equal to, since there is a negative, I can push the negative 1 over 4 inside this bracket out, okay, and I'll get negative 1 over 4 times 1 over 2 mu, so I get negative 1 over 8 mu del p del x and y max or y end square. Some books will use y end as in the end of the height, okay. So this will be my u max, okay. So always keep this formula in your mind. U max is always equal to negative 1 over 8 mu del p del x now times ym squared. The reason why I'm going through this with you is that once you know your velocity and you know the point where your u max is, always you can derive your u max, okay. Now let's go to what we call the tau max, meaning the shear stress mass, the maximum shear stress. Now if you go here, you know that shear stress is giving us what? This part, half del p del s, then times 2y minus ym, okay. So if I go, I just have to write this formula back, okay. You are seeing that shear stress tau is equal to half del p del x times 2y minus ym, okay. And we are saying that the shear stress also, the maximum shear stress occur at y equals ym over 2. So I have the maximum shear stress, this is supposed to be equal to half del p del x, then 2y is what, wherever I see y I put ym over 2 minus ym, then these two can cancel this. I have ym minus ym, which is 0, so I have everything to be 0. Actually it's not like it is 0. What this means is that when I come to the first slide, the shear stress occurs at the walls here of the plates, okay. It means it occurs at where you've never moved. So at the tangential places, that's where the maximum shear stress occurs, okay. All right, so let's move on to what we call the discharge. Actually the discharge KO here is giving us, KO is equal to please keep this in mind because we'll need them in our subsequent videos, u times a, okay. But in a continuous form it is u times the a, okay. All right, so let's keep this. Let me use a white pen for you. You said KO is equal to u times the a. The a here means that what area are we moving, and now you are saying that we are moving in a 1D, one-dimensional area, and the area is what with respect to y. So this will actually be equal to what u dy, since we are just moving in 1D. But our u is what? 1 over 2 mu del p del x, then y squared minus what? Ym y, okay, then dy. If I'm to be honest, the actual formula is supposed to be dko, okay, so that you know that dko is that. Then our k will be the integral of the whole of this, okay. So we count the integral of this whole expression here, 1 over 2 mu del p del x, okay, and y squared minus ym y, then dy. Now this becomes a simple integral for us because the 1 over 2 mu del p del x all becomes constant. So I have 1 over 2 mu del p del x out, the integral of y squared minus ym y dy. Now the question is, are you going to do this straight away just like that? No, because if you do it, it means we'll get a constant in this integration. But we know that we are moving. What is the whole limit of the y? if you go back to if you go back to our previous slide, the first slide that we have, y is moving from y equals 0 here to y equals ym, right? This side means that the entire length of y, or the area we move, is from 0 to y end or y max. Okay, so that will be the limit of the integration. Okay, so let me quickly erase some parts and we'll continue from there. All right, sorry, you have that. Let's erase it first. I hope you understand whatever we are doing, because it's very simple like that. Okay, now my K will be equal to 1 over 2 mu del P del X. Okay, then from, you are saying that you will have to integrate this whole thing from 0 to y max. Okay, so when I integrate y squared, what will I get? I'll get 1 over 3 y cubed minus, when I integrate ym here is a number. Okay, so I'll get the same ym, then y squared over 2. And we are saying that the limit of integration is from 0 to ym. Okay, so you can even put it here, 0 to ym, in your integral sign, 0 to ym. Okay, now let's evaluate this. Okay, evaluating it means that we don't need what is just here. You just erase everything and we'll write it there. So whatever value we get, or whatever answer we get here, will be our discharge. Okay, now if we do it clearly, you get KO is equal to 1 over 2 mu del P del X, then ym in place of every part. We have when we put 0 in, it will be 0, so we just have to put ym, and that will be our answer. So we get 1 over 3 ym cubed minus ym squared, because we are putting ym in place of y, over 2, and this is equal to 1 over 2 mu del P del X, then ym cubed over 3 minus ym cubed, okay, over 2. Now, so it's like this: 1/3 minus half, or 1 over 3 minus half, because they are all having the same numerator. So what we need to evaluate is just 1 over 3 minus half, and that will be 1 over 2 mu del P del X. Then we'll get what here? It's just negative ym cube, okay, over 6. Okay, that will be the answer for it. So let's erase the top here and write everything properly for understanding sake. Okay, all right, so that will be the discharge. Like I said, it's very simple like that. Okay, it's very simple. Once you understand it, you can derive the formulas yourself wherever you find yourself. Okay, just try to cope with it, and please don't chew. Okay, all right, so I have my discharge to be, now I have negative 1 over 6 here. I can just push it out of the bracket, and you come and multiply the half in front of this, and you get negative 1 over 12, okay, mu here del P del X, then ym cube. So this is our discharge for the whole flow that we are dealing with. Okay, now let's go to the next slide, and we'll discuss about what we call the U mean. Okay, now with the U mean is the discharge over A, where the A here is the area the flow is moving. In the area, I said earlier that it is what the dimension where we are moving, and the area is what, just one dimension. So the total area we are moving in is, we are moving in y. Okay, we are moving in y. Okay, so it means that we would have to ask ourselves, what is the total area we'll be moving in? It's just ym. Okay, so the total length for our y is what? Ym. So our u mean here is equal to the discharge over our ym. Okay, and this is equal to, discharge is what? Negative 1 over 12 mu del p del x, then ym what? Cube over ym, and this will give us what? Negative 1 over 12 mu del p del x ym squared. So this is what we call the u mean. Okay, the velocity mean. Okay, so you can always derive them yourself. Like I said, you don't have to keep them in your mind like that. So let's quickly consider the relationship between the u max and the u mean. Okay, if you remember, we said that our u max here, okay, is equal to negative 1 over 8 mu, okay, del p del x, then ym squared. And our u mean here, we just derived it, is equal to negative 1 over 12 mu here, then del p del x ym squared. So now with this, if I divide the two of them, you can see that there is a mu here, there is a mu here. Let me write it so that you understand what I'm trying to say. I have u max over u mean. Okay, so I have to save time, let me write it straight. Okay, so I have this u max over u mean, and this is equal to u max is what? Negative 1 over 8 mu del p del x ym squared over u mean is what? Negative 1 over 12 mu del p del x ym squared. So now there's del p del s, del p del s, ym squared, they will cancel off, and if you do the division clearly, the mu will cancel mu, and I'll be left with negative 1 over 8 divided by negative 1 over 12. The negative will cancel negative, so I have u max over u mean to be equal to 1 over 8 here divided by 1 over 12. Okay, now let me erase it, or let me come and write it here. So it's the same as 1 over 8 times 12 over 1. And now if I compute this from our basic understanding in division of fractions, what we will get is we'll get this to be equal to 4 goes here how many times? 2, and it goes here 4, so 3. So we'll get something like 3 over 2, which is the same as u max over u mean, meaning u max here, okay, is equal to 3 over 2 is the same as 1.5, so 1.5 u mean. Okay, so this is the relationship between u max and u mean. All right, so that is it for today. I just wanted to derive these formulas to you so that you know how they came about, because we'll be using them in our next video to solve examples. But to go, let's quickly discuss this. We have some types of para-viscous flow. You have the Poiseuille flow, co-edge flow, and then the combination of the two of them. In our next video, we'll discuss about what we mean by the Poiseuille flow, the co-edge flow, and then the combination. Then we come and solve the example I said we'll solve. Okay, thank you and see you next time.